Welcome to the proposal of Universidad San Francisco de Quito for the EcoConcrete Student Competition 2021. Team includes civil engineering students and environmental student Domenic Andrade, who studied and analyzed environmental impacts. Industry issues. Cement is produced at a global rate of 2 tons per capita. Mining for aggregates goes from 8 to 10% of global CO2 emissions, leading to soil exploitation. That is why there are SCMs that help us decrease emissions and increase durability. That's the goal of the competition, to improve concrete sustainability. The Ecuadorian company that will help us is Holcim, which has minimized their CO2 emissions in at 35% compared to Portland cement. Their energy consumption for clinker production is lower than the global average. This chart shows the CO2 gas emissions distribution for their cement production. For aggregates, we can have impacts regarding their extraction. Silica dust can be emitted during mining activities. That's why Holcim's quarry on P4 reducing at 10.3% the use of diesel, thanks to optimization processes in material extraction. For our SCM, we will use Adelca's blast furnace slag, which is a subproduct generated in the steel recycle process. Thanks to their production, we will decrease energy consumption in cement manufacturing.
Thanks, David. The selection of materials was focused on finding the ones with the most sustainable exploitation, fabrication, and transportation, reducing the environmental impact as much as possible. Geotype cement from the company Holcim was chosen due to the use of pozzolan as one of its components, giving it increased durability and a better defense against chlorides and sulfates. It also reduces CO2 emissions by 35% compared to the production of Portland cement. Holcim accomplishes the following normatives and regulations. Holcim also provides our aggregates, since their mine source is just 19 kilometers away from our lab. They have active plans to reduce their ecological footprint, such as recovering 104.5 hectares of its exploitation area, planting 2,950 trees, investing $1.5 million to boost the use of clean energy, and optimizing the raw material extraction. Finally, slag was chosen as our supplementary cementitious material coming from the company Adelca. The use of slag has positive effects. The first one being improving our environmental engagement by using a byproduct generated by the iron industry. It also gives our mix high durability and a better performance against chloride attack as presented in the written report.
The parameters for the design were chosen obeying the results of different research papers. The cost-to-fine ratio was taken as the upper limit of the suggested ratio obtained from saline environment tests of strength, durability, and chloride resistance. This upper limit was chosen because results from research papers with cost-to-fine ratios between 1.8 and 1.9 showed an excellent strength performance, but these studies did not test their samples under saline conditions. The cement content was obtained by averaging the results from one research stating that the best performance was with mixtures containing 350 kilograms of cement per cubic meter, and another having samples with an average of 366 kilograms per cubic meter, that reached 100% of the expected final strength at an age of 28 days. The water-cement ratio was set in the competition rules, while the proposed air content was obtained by averaging the results from graduate thesis and laboratory reports from students at the university. The final concrete mix design is presented here. The same amount in kilograms of cementitious materials, water, and aggregate per cubic meter was used as shown in graphs 1 and 2. For the alternate case mix design, 40% from the overall cementitious materials were replaced with slag, corresponding to a 5% in mass from the overall mix design. Regarding volume, its distribution changed consequence of the presence of slag in the cementitious phase. The loss of volume was compensated, increasing the air content from 2.3% to 2.65%. In the following slides, Marco will mention and discuss the results of the alternative case scenario mixture and its benefits and advantages in comparison to the base case scenario.
In durability and performance, the particle size distribution of the mixture resulted in a smooth grading curve that meets allowed limits based on the characterization of coarse and fine aggregates from Holcim. But the coarse aggregate is the common variable that gives durability principally to the base case and reciprocally to the alternative case, due to its 23% mass loss in abrasion test along with its spherical and rounded shape. With this mentioned data, now it's necessary to justify the difference between the alternative case and base case in terms of durability. And the answer is the improvement gained substituting geocement with the slag, whose selection was developed considering its availability in the country and the pollution it generates through production processes of the factories. The addition of the GBS gives an optimization of the pore structure and size distribution, densifying the mixture, making it less permeable to external agents and reducing the risk of sulfate attack, alkali-silica reactions, and chloride penetration. Tests implemented to measure the chloride permeability and corrosion rate were developed, such as the rapid chloride permeability test that resulted in a reduction of the total charge passing through the concrete. That means a better resistance against chloride ions. And the electrical resistivity tests shows a reduction in electrical resistivity. That means a lower corrosion rate. Based on the mentioned properties, the Live 365 software calculated an improvement of 6 years between the 11.9 years for base case and 17.9 years for alternative case in chloride penetration propagation, a fact that increases the service life of the mixture against chloride exposure.
Thanks, Marco. Here is presented the life cycle assessment result for the crowd-to-gate approach. An overall improvement is shown in all categories. Nevertheless, global warming, ozone depletion, and fossil fuel depletion show the largest improvement. In the case of global warming potential, reduced carbon footprint of slag production decreased significantly the impact for concrete mix in this category. For fossil fuel depletion, the use of this resource have larger impact in cement production as larger quantities of fossil fuels are needed for the clinker manufacturing process. Now, carcinogenic, ecotoxicity, and also depletion impacts have a better improvement thanks to the proximity of the slag supplier to the USFQ plant compared to the cement plant. This highlights the importance of using locally available materials as shorter distance represent lower consume of fossil fuels and the impact associated with their issue. These results give a general idea of environmental impacts when designing a concrete mix. However, more exact view of environmental impacts will be achieved by using local factors in the tools database, since variables may differ within each country. This concludes our presentation. Thank you.